So now I'm going to talk about the generation and detection of Amv. So first thing that we get here is a square law modulator. In generation, square law modulator. So what happens in a square law modulator is that we pass the signals, which is the carrier signal plus the message signal. Always remember, here we don't pass the product, anything. We only pass the sum of the two signals through a square law modulator, which can be of any variable multiplier, like it can be a naught into vi plus b naught into vi square. It can be anything like this. So the output given v out is passed through a band pass filter, and the output is given. But the thing that I used to forget was this, that we give the sum of two signals, ct plus mt, and after passing this we can obtain the output, which would be obviously a modulated signal. I won't derive the exact equation. So this is the equation that we obtain after solving. You need to remember only this: 2b by a is equal to mu here, where b is the one with vi square and a is one with vi. So there's an easier method. If you get anything except this a naught vi plus b naught vi square or a vi plus b vi square, anything except this, what you need to do is you need to put the input as ct plus mt and solve everything and pass it through the band pass filter and derive it. But most probably you will get a question related to 2b by a. Now comes the method for demodulation. Demodulation is comparatively easy and requires similar method like square law modulator for modulation. Similarly, square law demodulator for demodulation. So what happens here is we give a signal which is received a square law device. Square law device is a nonlinear device again, which can be anything like uh, AVI plus BVI square. It can be anything, and it is passed through a low pass filter. So what is the thing you should remember, that while modulation you use a band pass filter, whereas while demodulation you use a low pass filter. So after passing the signal you can obtain the output, and important thing here is that which is also asked in various previous year ISRO exams, that what is the signal to noise ratio in a square law demodulator, and the signal to noise ratio is given by 2 by ka mt, or you can write max value of mt, which is also 2 upon mu. So if you are ever asked what is the signal to noise ratio, signal to noise ratio in a demodulated signal, in a demodulated signal, for a square law demodulator, it is given by 2 by mu. You need to always remember this. This can be easily solved by directly putting the things in the formula. The second is the envelope detector. Envelope detector is something like this. You give a signal, pass it through a diode so that only positive values pass. A capacitor is used in parallel to the output RL, from which the output is obtained. This is capacitor C. So the thing required here is that I show you graphically. So if this is the signal, and you pass it through a envelope detector, what will happen is your your output will move along with the sinusoidal signal, and once it reaches the maximum value, the capacitor is charged, so capacitor just discharges slowly and it moves like this. Now capacitor again charges and discharges again, charges and discharges again, charges and discharges again. So how this is helpful is, so now let us assume again the, I'm again taking axis. So let this be the boundary. Similarly, this be the boundary, and we have a carrier signal which looks like this. So the amplitude of the carrier signal is being modulated, and you need to obtain the output. So what will happen? The capacitor will charge, discharge, charge, discharge, charge, discharge. It will charge very quickly but discharge slowly. Charge quickly, discharge slowly. Charge quickly, discharge slowly. Charge quickly, discharge slowly. Charge quickly, discharge slowly. Similarly, this will happen throughout. So what you will obtain is, if I erase this part, if I erase this part, you can see that almost the message signal is being obtained, and it can be passed further through different filters to obtain a proper message signal. So I think you must have understood how this works. Now I'll explain you the different numericals that come through this part, and this is the favorite part of ISRO. Like most of the questions are from this part. In detection, like you'll have FM detection, you'll have FM generation, AM generation, but most of the questions asked in the previous year questions were from the envelope detector part. So if you take a look at it, you will see that um, you need to charge it very quickly. Charge quickly, but it should discharge slowly. Okay. So what? How do we manage this, and how do we do all the things related to it? It is done by slowing down the discharging time. So your discharging time and charging time can be obtained very easily. I'll show you. Like, let us assume that uh, this is the source resistance RS. It had been sometimes asked along with the resource resistance, that what should be the value of source resistance, or what is the value of capacitor if the value of source resistance is this. Except load resistance, source resistance is also required but sometimes ignored. So if RS is the source resistance, the charging time should be very quick. Charging time should be very quick. So RS into C, which is charging time, should be very less in comparison to the frequency of the time period of the carrier signal. Similarly, the discharging time should be very large than the message signal. So discharging time is given by RL into C, because it is on the load side, charging is on the source side. The while charging, the source resistance is taking part, while during discharging the load resistance is taking part, and it should be very less than the message signal. So I'll explain you why we take into consideration the message signal, why we consider the message signal here, why it should be less than message signal. It can be explained with the help of concept of diagonal clipping. So what happens sometime is, like, if you I should explain you again graphically, it would be easier. This was the carrier signal which was modulated like this was the message signal, and it had been modulated. The carrier signal had been modulated along the amplitude of the message signal. So now, while charging and discharging process, like charging, discharging, charging, discharging, charging, discharging, sometimes what happens is the discharging is so slow that it skips some of the message signals. So this entire part had been skipped because of very slow discharging time. So in order to avoid this, we want that the discharging time should be slow, but it should not be slow than the uh, message signal. If it is slower than message signal, then diagonal clipping would occur. So the best way to remember it is that uh, I used to forget that we have chart where we have the message signal, where we have the carrier signal. How to remember is that what is the most important thing? The most important thing is the message. So it is at the maximum time period for the message should be at maximum because it is the most important thing. We need to obtain the message signal after modulation. So message signal should be the maximum. And what is the other thing that is less important is the carrier signal. So it is the least required. It is never asked, not much asked about RS and uh, the source resistance and the charging time. So what should be in between? RL into C. So always require message signal is the most important. So it is the maximum, and least is the carrier signal, and time period of the carrier signal, and RL into C is in between. Now, if you need to find the exact value of what should be the value of RL into C, so it is given by RL into C is should be less than equal to 1 upon omega m under root 1 minus mu square into mu. So this is very important. Asked in previous year ESC questions and ISRO questions. How to find the, so they'll ask what should be the value of RL, what is the value of C, if the um, frequency of message signal is this, if mu value is this. So you should know that RL, I'll write it again, RL into C should be less than equal to under the root 1 minus mu square upon omega m into mu. So mu should be less than 1. This is valid for under modulated signal. Always remember, you can never use envelope detector for overmodulated signal. There is only one method for overmodulated signal, and that is synchronous detector or coherent detector. So if you are ever given mu value is greater than 1, how to know mu value? So it is 1 plus AC 1 plus mu mt cos 2 pi fct, or it is mu into mu is k into maximum value of mt. So this is the rest value of mt. So this is the value of mu. So if you are given a sinusoidal signal, it would be mu sine omega mt, and this will be the value of mu. It should be always less than 1 if you need to use anything related to envelope detector, but if it is greater than 1, you will use synchronous detector, which is also known as coherent detector. Don't forget this, because in question that is mostly asked, you are given a coherent detector and student get confused that what is a coherent detector, because everyone has always studied a synchronous detector. Like in my college, I had studied only synchronous detector. I was knowing that there is something called coherent detector, so I got confused. So what happens in a synchronous detector? You take the message signal and you multiply it with by the carrier signal again, AC cos 2 by FCT, and then pass it through the low pass filter. So how to remember different things that whenever you are doing detection, use low pass filter. Whenever you are generating, use band pass signal, band pass filter. This is a must. You must remember this. Like sometimes while you see the question, you get to know that this is a detector, this is a generator, only by seeing that there's a low pass filter on or a band pass filter. So after multiplying these two, you what you get is again multiplying the cos signals and passing to the low pass filter having frequency of FM. What you get is AC square Ka mt by 2 into cos of theta. This is what you obtain. And why is this cos theta? Because there is a phase difference between the carrier signal and the message signal. So after you obtain this, you'll observe one thing. First of all, how to remember this? What is AC square by 2? Power of the carrier signal. AC square of 2 is power of the carrier signal. It is multiplied by Ka into mt. I used to remember it like this because it is very easy. Like how to find the output from a synchronous coherent detector. It is power of the carrier signal into Ka into message signal into cos of theta, where theta is the phase difference between the carrier signal applied and the message signal. So what happens because of this cos theta? So you all know that if theta is equal to 90 degree, cos 90 degree is 0 and we'll get 0 output. So whenever the whenever the phase difference between message signal received and the carrier signal is equal to 90 degree, you don't get any output, and this is known as quadrature null effect. Quadrature null effect. You need to remember this concept, quadrature null effect. So these are the major methods that you require, and now in the next video we'll talk about Hilbert transform and how it is used in the DSBSC, SSBSC, and move further using these concepts. So I think you like the video and you get to know what you need to study and what you don't, because I got this information all by my research work, and I think it would be helpful for you. Thank you.